All right, today we're going to talk about using scientific measurements. Okay, so we've talked a little bit about scientific notation. Now we're going to talk about scientific measurements, things like error analysis and how things move. All right, so if we start to flip through, one of the first things we need to define is what's called accuracy versus precision. Now, there are two terms that, we've talked about this a little bit, have common names, but now we want to make sure we define their scientific name. Accuracy is going to be the closeness of a measurement to the correct or accepted value. Okay, the accepted value. You can use highlighter if you want to for any of these words that I'm highlighting or circling or underlining or circling. The highlighter just isn't working right now for me. Okay, then we have precision. Precision, rather, is the closeness of a set of measurements, or what we refer to, I like to refer to as repeatability. I think one of the best ways to explain that is a bullseye. Okay, over here you have the bullseyes, or rather the darts that didn't even come close to the target and are all over the place. So they have both low accuracy and low precision. Now this one I think really defines the difference. You have three darts that are relatively in the same area on the bullseye, but not, again, not close to where they want to be. So they have low accuracy because they're not near the target, but they have high precision because they are near the target. Remember, precision is going to be repeatability. Okay. Now, I don't know that I totally agree with this one. It says it has high accuracy, maybe because it's close to the bullseye. I don't think it's very high accuracy, but I didn't draw the picture. So higher, I guess we could say higher accuracy than this one because it's closer, but still pretty low precision because they're all over the place. Whereas over here we have, excuse me, three darts that are all right on the center, all in the same spot. So this is what we like here, right here, high precision and high accuracy. Now, whenever also we talk about how wrong you are, a lot of times we're going to do what are called percent error calculations. And percent error measures the accuracy of an experiment. So how close you are to the right answer. Right? That's what accuracy is, or how close you are to the right target. Now here we're measuring the accuracy of an experiment, and we're going to do this with a density of metals lab. Now I do want to remind you, it can be either positive or negative, one or the other. Okay, one of those two. Sometimes you get negative percentage and everyone kind of goes, wait a minute, what does that mean? And I'll show how we get there. This is the equation. You have the experimental value minus the accepted over the accepted times 100. A lot of times you will see me abbreviate it as experimental minus accepted over accepted times 100. Just because it's a lot to write out. So anyway, that's going to be our equation. Now we're going to go ahead and do a math problem, and I'm going to go through the requirements of a math problem when we solve them in chemistry. The first thing we have to do is list out what's called the known and the unknown. So you're going to put two columns out here with a K and a U. And in the known, actually that's a little bit tight here, so I want to be able for you guys to see it. Let me do the known first, and then I'll put my unknown. Anyway, my known values is what the problem tells me. So if I read the problem, it says the measured density from the lab experiment is 1.40 grams per milliliter. Now when you do the known, you can't just write the numbers, you have to tell me what it is. So if it's measured, measured is another word for experimental. So my experimental value is going to be 1.40 grams per milliliter. The correct density, all right, correct, another term for correct, is accepted. The accepted density is 1.36 grams per milliliter. Okay, so I'm going to scoot that out a little bit here. My unknown is what I'm looking for. I want to know the percent error. So what I'm looking for is percent error. Okay, so step number one is always going to be to write out the known and the unknown. Step number two is going to write in the equation. So from the last slide, we know that our equation is experimental minus accepted over accepted times 100. Okay, so that's what I mean by writing out the equation. Then we're going to do the work. So we have to plug the numbers in. Remember, you should be writing all of this down. So 1.40 minus 1.36 1.36 over 1.36 times 100. Now, I want everyone to get their calculator out because I guarantee that some of you will make a mistake when you do this on your calculator. When you type this in your calculator, go ahead and put 1.40 minus 1.36 and hit equals. Okay, you should get 0.04. Okay, so 0.04. Then you can do the rest of your problem. So you take 0.04, divide it by 1.36, and multiply it by 100. Okay, so I'm going to go ahead and write down two decimal places, and I'll answer that question as to why here in just a minute. But we get 2.94% as our answer, meaning that 1.40 is 2.94% higher than 1.36. Since it was a positive number, that means that the experimental was too high. If you ever get a negative number, it's going to mean the experimental was too low. Not one more correct versus the other, but when you have negative and positives, that's just what it means. And we'll do more of these in class. Okay, now we're going to talk about what are called significant figures, and I'm going to guarantee or warn you that you're going to be very confused. We're going to do lots and lots and lots of practice in class, and hopefully it will make more sense. Okay, significant figures are all certain digits plus one estimated. And where this comes from is the technology that we use in class. Okay, we are at limits in the technology that we have available to us. For example, this is a 10 milliliter graduated cylinder. And that graduated cylinder has increments of 0.1 liters. We could also estimate one more decimal place, or how far in between this is, and that's where we get our estimated digit. Same thing over here. This is a thermometer, and you can see this would be 41, 2, 3, 4, 5, 6, 7, 8. It's definitely between the 8 and the 9. You can kind of see, I think it's closer to the 9, so I might estimate this as 48 let's say 9 degrees Celsius. Okay, and that's my estimated digit. That's what I'm talking about, and we'll do this a lot in lab. Okay, another good example is over here, where you have, this is a 100 milliliter cylinder, and it's only giving you to the tens. So I definitely know it's 60. You estimate how far in between. Whenever we read a graduated cylinder, we read the bottom of the meniscus. We'll do this later. So I'm going to say that this is, we know the 60 is a definite, but I'm going to say 63, and that is my estimated value. Okay? All right, so determining the number of significant figures. All non-zero numbers are significant figures, so 3s, 7s, 8s, 2s, whatever. Zeros are where things are going to get confusing. And again, just know in this video, you need to just listen, process, write it down, and we'll get a chance to do a lot more practice in class. Leading zeros never count, okay? Never, ever, ever count. They are just holding places, and you can get rid of them with scientific notation. Embedded zeros always count. Embedded is a fancy word for in the middle. So if you have a 0 in the middle of a number, it's going to count. Now, trailing is at the end, and these are going to have a couple of different rules. Only counts if there's a decimal point. So, let's see. Remember, embedded are between non-zero numbers, just a repeat. All are sig figs. Leading are all out in front. None are sig figs. We like these rules. All and none. Those are nice, meaning they make our lives easier. Trailing is when it's a little bit more confusing. If there is a decimal, then they count. If there is not a decimal, then they do not count. Okay, what the heck does that look like? All right, let's see how many significant figures are in these numbers. All right, first off, you have 5 numbers that are shown here. Both of these zeros are what we refer to or embedded, or in the middle of a number. So all 5 of these numbers are going to count. 1, 2, 3, 4, 5. So there's going to be 5 sig figs in this number. Okay, then we get 20.0. Now these zeros are at the end, so this is going to be trailing. So they will count. So it also is going to be 3. Now, if it was written as 20 without a decimal place, it would be trailing with no decimal place, so this would only be 1. Again, don't panic if you don't totally understand it right now. We're going to do practice in class. Okay, here we've got two types of zeros. We have leading, and then we have embedded. The leading ones, I always remember, if you can cross them off at the beginning, they do not count. They're just holding a decimal place. So this is going to be 4 significant figures because this 0 will count. Here we have 17,000 trailing, meaning at the end. First off, no decimal places. So the way this is written is 2. If I put this decimal place right here, it's still trailing. They now do count. 1, 2, 3, 4, 5. And I'll explain a little bit more about what it means to count or not count and why that's important. Okay, here we also have trailing. We also have a decimal place. So these are going to count. So this one is going to be 4. Oops, if I go back for just a sec, if this one did not have a decimal place, if I wrote it as 4,320 with no decimal place, then it would only be 3. Okay, again, lots of practice in class. Okay, we also need to be able to round when we write a calculation, and our calculator gives us lots of what we refer to as insignificant figures. When rounding, you always want to look at the digit after the one you can keep. We go with the same old rounding that we've been doing for a long time. Greater than or equal to 5, we round up. If it's less than 5, we keep it the same. Okay, so 761.5 would be 762. Because that 5 is going to round it up. 14.334, we can only keep the first 3. This 3 right here is less than 5, so it's 14.3. 10.4, again, we can only keep 3. This is less than 5, 10.4. Okay, then we get to the tricky ones, 10,789. Okay, I know that this is going to round this to is going to end up being 108, but I can't just write 108. It has to be 10,800. Now I can't put a decimal place because that'll make it 5. So the only way I can write it is with scientific notation, which is going to be 1, 2, 3, 4. So it's going to be 1.08 times 10 to the 4th, because when we write scientific notation, we use the same rules. Okay, same thing here. We have 8,020. And we can write it just like this because without a decimal place it only has 3 sig figs, or 8.020 times 10 to the 3rd. And again, this will take practice, but at least you're hearing it for the first time. Alright, this 5 is going to round that up, so 204 would be my right answer. I actually could also do 2.04 times 10 to the 2nd. Okay, now I'm going to run through calculations pretty quick, and we'll do a lot of these in class. Adding and subtracting, you always want to end with the least number of decimal places. So the easiest way to do this is to draw them in good old-fashioned arithmetic form and put a line, and you'll see me do this all the time. The last number I can keep here is the 8. I do still do the math. This will round up to the 9. Okay, so it's explaining that out here. And this is also just another simple version. If I take 4.8 minus 3.965, I still do the math, only 1 decimal place. So my answer can only have 1 decimal place. And so after I do it and I round, 0.8 is my final answer. Multiplication and division is much easier. You just use the fewest number of sig figs. So this one has 3, this one has 3, this one has 2. So when I do my math, I can only have 2 sig figs, and I have to write it as 5.0 times 10 to the 2nd. I have no option there. Again, I know I'm going fast, but I'm running out of time. And then last but not least, same thing. This one has 3 significant figures. This one has 4. So when I do my math, I can only report 3. Okay. I hope that helps. We'll do lots more practice in class. Good luck.